All right, here we go. New chapter. We're starting chapter 4, and we're still talking about derivatives, guys. Chapter 3, we mostly focus on finding derivatives. We'll use them a little bit here and there to tell us things like slope of the tangent line and rate of change. But in this section, we're really going to focus on, okay, we know how to find all these derivatives, but how can we use that information? How can we use the derivatives to tell us even more information about, say, the function or the graph? So we're just going to be using these derivatives and putting them to work for us. So remember that the sign of the derivative can tell us whether a function is increasing or decreasing, because the derivative really tells us rate of change. So if we have a positive derivative, that means we have a positive rate of change. That means our original function. So I want to draw this distinction. Here we're comparing the sign of f prime of x. We're comparing the sign of the derivative with the original function. So if the derivative it has a positive sign, that means my original function is increasing. And I may not know how quickly it's increasing, but I know it's increasing in some way. So perhaps it's just a straight line, or perhaps it's curving upward or downward. We'll talk more about that in the next section, but I know at the end of the day that my function is increasing. If, on the other hand, the sign of f prime of x is negative, that means I have a negative rate of change. That means that my original function, f of x this time, is decreasing. So my function is decreasing, it's going down. Again, here we might have a straight line, we might have a curve downward or a curve upward. That one's, I think, a little bit harder to visualize. But we'll have something that is, at the end of the day, decreasing here. So we're going to look at a lot of examples involving the sign of the derivative. That's really what we're interested in today. So let's look at a pretty quick example here. First, I'm going to work with f of x equals 8x minus x squared. I want to start by finding the derivative, and okay, that's not too bad. F prime of x. This is just a power rule to find this. I don't need a product rule or a quotient rule or a chain rule here. My derivative should be 8 minus 2x. So okay, there's my derivative. That wasn't too bad. Next, I want to find the x values where we have a horizontal tangent line. So remember, we see this horizontal tangent. What that really means, if I have a horizontal tangent line, first of all, tangent line makes me think about the derivative, and horizontal, if I have a horizontal line, I know that the slope of that line is 0. So I'm taking my derivative, f prime of x, setting it equal to 0, and solving that equation. So my derivative from the last part, 8 minus 2x, will set that equal to 0. So 8 equals 2x. Means that x is equal to 4. So at x equals 4, we have a horizontal tangent line. Actually, I just can't quite. Let's just rewrite that so it's a little bit easier to see. At x equals 4, I have a horizontal tangent line. So that's very cool. But this is all stuff that we've seen before, right? We've found the derivative using the power rule. That goes all the way back to chapter 2, and we've talked about horizontal tangent lines. We saw that in chapters 2 and chapter 3. But here's where something new is happening. I want to know, where is f of x increasing and where is it decreasing? So there's a few different ways that I could go about this here, and we're going to spend a lot of time with these two questions. I think that this is a really important question. I'm going to organize my work in a way that should hopefully feel familiar to us, because we actually did something similar when we were solving inequalities way back in chapter 2. I'm going to create a number line over here, so f prime, and I'm going to make this number line. Now I know that the derivative was 0 at x equals 4. So x equals 4, this seems like a pretty important point. I'm going to say at x equals 4, So there's my x's. I'm going to have the x's be below my number line. I have a derivative f prime of 0. So I know that the derivative is 0 exactly at 4. And essentially what I've done is I've broken my number line up into two parts. I've got all of this area to the left of 4, so this represents all numbers that are less than 4. And then I've got all this space over here to the right of 4. These are all numbers that are greater than 4. So what I want to do is I want to use this information that we gave earlier. We're going to look at the sign of f prime of x to talk about where f of x is either increasing or decreasing. So we can do this a few different ways. We can set up an inequality. My favorite way to do this, though, is I'm actually going to take a number. So let's start with this left-hand side. I'm going to take a number on the left-hand side of 4. So any number that's less than 4 will be just fine. So we could pick x equals 3, we could pick x equals 2, 1, 0, -1, any of those are just fine. I'm going to pick, how about x equals 3, and I'm going to plug that into my derivative because I want to know, hey, what's the sign of f prime of x? So f prime of 3, I'm going to plug that into my derivative. Now our derivative, we said that was 8 minus 2x. So this is 8 minus 2 times 3. This is 8 minus 6, gives me a positive 2. The number itself is not terribly important. What's really important is the sign of that number. Here I have a positive 2. So what does that mean? That means I have a positive on the left-hand side of 4, which what does that mean? We said if f prime had a positive sign, then our function was increasing. So that means what I like to do is on my number line, I'll put these little plus signs right here, but I'll also put a little increasing line. I think that's really helpful. Now, you might have said, well, what happens if I didn't choose 3, right? What if I chose, you said I could choose any number on the left-hand side of 4. What if I picked 0? Well, that's just fine. Let's see what would have happened if you would have picked 0. You'd have 8 minus 2 times 0. I've got 8 minus 0, which is 8. Remember we said the actual number itself that you end up with is not particularly important. It's the sign of that number. I ended up here with a positive 8, so I would still have a positive number on the left-hand side of 4, which tells me my function is still increasing on the left-hand side of 4. So the number that you pick on the left-hand side of 4 isn't terribly important. No matter what you pick on the left-hand side of 4, we should end up with a positive result. So if you pick a different number than me, that's okay, but the numbers, when we take our numbers and plug them into our derivative, we should end up with the same sign, either positive or negative. Now I'm going to do the same exact thing, but now I'm going to look on the right-hand side of 4. So I'm going to pick a number that's larger than 4. 5, 6, 7, 8, 9, 10, any of these will be just fine. So I'm going to take 5, let's say, and plug that into my derivative, f prime of 5. So that's 8 minus 2 times 5. This is 8 minus 10. This time I have a negative 2. So, okay, negative 2. What happened if our derivative was negative? We said, hey, if the sign of f prime of x is negative, that means that my function is decreasing. So I'm going to make two little notes to myself on my number line. I'm going to put a minus sign. Sometimes I'll put multiple minus signs. Sometimes I'll just put one big minus sign. But then I also want to make a note to myself that, hey, that function is decreasing over there. So I'm going to draw in just a little decreasing line, just so that it helps me remember what a decreasing line looks like. It'll also help me with the next part of my problem, which we'll get to that in just a second. The last part of this, though, is I need to determine where it's increasing and where it's decreasing. Because what I've really done is I've broken my number line up into two chunks. We said we've got this area over here to the left of 4. So that area, that interval, is negative infinity to 4. Now we're not including 4 because we said the derivative was 0 exactly at 4. It's technically neither positive nor negative. And if it's not positive, it's not increasing. If it's not negative, it's not decreasing. So 4 is something kind of interesting and special is happening at 4. And then we said, okay, we also have this area over here on the right-hand side of 4. Again, I don't want to include 4, so I'm going to use parentheses, 4 to positive infinity. So that means, hey, if we look at what's happening on negative infinity to 4, well, our derivative was positive, so that means our function is increasing on that interval. So our function is increasing on negative infinity to positive 4. Over here on 4 to infinity, we said we had a negative derivative, which means that our function is decreasing. So our function is decreasing on 4 to positive infinity. So we know exactly we know exactly what x values that f of x is increasing on and where f of x is decreasing on. So earlier in chapter 2, I said, hey, interval notation is going to be really important, and here's where we're going to use it a lot. We're going to use it a ton in this section. So, or rather, this whole chapter, we're going to be using it quite a bit. So, make sure that you're familiar with interval notation. If not, let me know, and we'll hopefully get you up to speed on it. Lastly, part D, we're going to see this quite a bit here too. Sketch a graph of f of x, because it'd be really nice if I could actually use this information about where my function is increasing and where my function is decreasing. If I could put all of that to work to give me just kind of a rough sketch of f of x. Doesn't need to be perfect, but I'd like an idea of what is happening. And this is a nice equation to start with because it's a relatively simple function, and actually because this is a quadratic, we can actually already look at it and say, okay, we've got a quadratic equation, which means we have a parabola, and the quadratic term has a negative coefficient, so that means we have a parabola that opens downward. I don't know anything else about this, but I know that it's going to have this general shape. So, for reasons which will become clear later on, hopefully this number 4 right here stands out as being really important. It seems to pop up a whole bunch here, and a lot of our answers are kind of revolving around this number 4. So what I'm going to do, I don't need to take a ton of points and plug them into my function. I don't need to know exact coordinates of a lot of points. But this 4, boy, it's popping up all over the place. That feels like a really important point. So I'm going to take x equals 4 and plug that into my function because it seems like there's a lot of interesting stuff happening there. So I'm going to take 4 and plug that into my original function. F of 4 is equal to 8 times 4 minus 4 squared. So let's see, this is 32 minus 16 would give me 16. So that means I have a point at 4, 16. It's okay, I don't know exactly what's going on there, but I know that seems to be an important point. Let's just go ahead and plot that point. So I've got a point at 1, 2, 3, 4, and let's do 2, 4, 6, 8, 10, 12, 14, 16. We've got a point, let's say right around here. Now, why was that point important? I think it's important for 2 reasons, really. First reason was we said, hey, at x equals 4, you've got a horizontal tangent line. So sometimes what I like to do when I'm drawing these in is I'll actually sketch in the tangent line. I know that I should have a horizontal tangent line right there at 4. And I think that'll help you create this graph a lot. Why else was 4 interesting? We know we have that horizontal tangent line right here in red, but why else is it important? Well, look at part C. That's where it changes from increasing to decreasing. I'm changing from, my function is sort of switching gears. It's increasing on the left-hand side, it's decreasing on the right-hand side. So hopefully that gives me enough information that I can kind of draw out this graph. My function, it's increasing on the left-hand side, and I know I have this horizontal tangent line right here. So what that means is I should have kind of like a nice smooth top to that curve. And we know that that seems to make sense because we said, hey, this is a parabola. It's a parabola that opens downward. We must be talking about this point right here. So on the left-hand side, it's increasing. Probably looks something like this. And then on the right-hand side, after that, so after we have that horizontal tangent line, what happens? Well, it's decreasing. It's going down. So, okay, after that, my function decreases, it's going down, and it looks something like this. And hey, I see that upside down parabola, or that parabola that opens downward. So this is a really nice example. I think it's pretty good to follow just because we know already how this function behaves. We sort of know the answer. We can sort of check our answer at the end of it. And it seems like, yeah, all this calculus we did here with part B and part C really did help us construct this graph here. So sure, we could have done this with, our vertex formula, but what if we have more complex functions? What if I have a cubic function or a quartic function? It'd be really cool if I could sketch the graph of those functions without using a graphing calculator, and that's kind of what we're going to focus here in on this section. So a lot of our problems are going to follow this very similar template. So this is a really good example to fall back on if you feel a little bit stuck later.